Hello, welcome back to the channel, and I thought I'd continue my series explaining how devices such as solar panels, batteries, heat pumps work, and create a sub-mini series about solar panels. So before we continue, please make sure you hit the subscribe button. It helps me grow the channel and helps this information be spread wider afield. So, if you watch my previous video, and I'll put a link to it up here, you'll see that I've explained how a basic solar panel worked, where you take silicon, and you take two varieties of silicon, one which has been doped with phosphorus, which makes it N-type, so it has excess electrons, and one doped with boron, which makes it P-type, which means it has an excess of holes. And when you sandwich those two materials together, you create a depletion region as those excess of holes and electrons try to neutralise, creating a region where charge can't flow. And when light hits this depletion region, those electron-hole pairs will split apart. The electrons will move towards the negative or the N-type material, and the holes will move to the negative region, so you get an inbuilt voltage and you get a flow of current when light hits, and that's the basis of a solar panel or solar cell. So in this video what we're going to do is look at the limits of silicon solar panels. And this is important because pretty much every solar panel you will see on somebody's house or in a solar park, so if you're driving down a motorway and you see a field full of solar panels, all those solar panels are made out of silicon, and they all rely on the same technology that I've explained in that previous video. However, if you are doing some research or just looking into solar panels, you will see, first of all, people talking about different types of solar cells, such as perovskite or dye-sensitized solar cells, or multi-junction solar cells. And these emerging technologies, and I'll follow this video up with more in this mini-series that explains each of those and what's their pros and cons. And you'll also see information about the limit of silicon solar cells and their efficiency. You might even see the NRAL graph, which I'll just put up on the screen now, which shows the maximum efficiency being achieved by research for all these different types of solar panel technology or solar cell technology. So a number you'll see bandied around is that silicon has a maximum efficiency of about 33%. Depends on where you take your sources from. Some say as low as 31. If you look at the Wikipedia article, you'll see 33.7%. And you'll also see a term called the, and I've struggled to say this, it's the Shockley-Queisser limit. So Shockley and Queisser are two semiconductor physicists, and in the 1960s they calculated the maximum efficiency of a single junction, so this is where there's just one N-type and one P-type junction solar cell. And this number gets bandied around for the reason for these emerging technologies in solar cells, because you need to, if you want to get more efficient solar cells, you're going to have to look at technologies outside single junction and outside silicon. So what you might be trying to work out is what this limit is and where does it come from, and why the solar cells we have at the moment on our roofs are not 33% efficient. They're about 20 to 22% efficient. So I'll go over this in this video. So let's just talk briefly about the Shockley-Queisser limit. So there is some quite heavy-duty physics involved in this, but effectively what they do is, or what Queisser and Shockley did, was combine some different ideas to try and form this limit. And it is complicated because not only are you dealing with electrons that are being split apart by light, so you're having to deal with the interaction between light and the electrons, and that's statistical, so sometimes the electron will be excited, sometimes it won't. You have to deal with something called recombination, which we'll go through, then the electrons moving through a semiconductor, resistance at contacts, so it can become quite complicated. or quite a complicated system, and therefore making a complete prediction is very difficult. However, what is included in the Shockley-Queisser limit, is, first of all, something called black body radiation. So this is the idea that any light or any radiation hitting a subject, some of it will be absorbed and then it can be re-emitted. If it's a black body, all of it will be re-emitted. So in the case of a solar panel, the light will hit it, it'll be radiated, and about 7% of that energy will be re-emitted by the solar panel in the terms of heat coming off, i.e. that would be the black body radiation, is that energy coming off. And I say it's about 7%, so you get some losses due to this. You also get a type of recombination occurring. So there's multiple types of recombination that occur. And what I mean by recombination is, if you remember back to my previous video, you have a electron hole pair, and when the light hits it, that pair splits apart. So you're taking in radiation and you're getting electrons out effectively, as that electron hole separate. But the opposite is true. What you can get is the electron recombines with a hole. It doesn't have to be the same hole, and gives out light. And this means you're taking away from the electrical potential or electricity potential that can be generated, and we end up with light coming back out. And this effect is mainly dependent on temperature and how that temperature affects the semiconductor as a whole. So when the light hits the solar panels can get quite hot. So you probably have noticed that the efficiency of solar panels drop as the temperature increases. And if you watch some of my previous videos where I'm talking about my own experience on my own solar panels, you'll have seen a video where I think that in the height of summer, even though we've got full sun, my solar panels are about 15% less efficient. So I'm not hitting the maximum voltage that they should, maximum wattage they should be producing. And that's down to the heat. Because there's a number of ways of looking at these. Some people will explain this as the band gap of a semiconductor effectively getting smaller when the heat goes up. Or it can be thought about as electrons in the valence band being promoted up to the conduction band more easily because they can take on that heat. It's a bit like applying a voltage. And what this means is that you can get current flowing in your solar cells more easily because you promote more carriers. And this is something you don't particularly want inside the solar cell just when it's generating electricity. What you want to do is have a large, what's known as an open circuit voltage. So this is the voltage that the solar cell will generate when light is hitting but no load is applied, which means that the current isn't really flowing. However, so effectively you want a high resistance within your solar cell. However, those increasing carriers means that the resistance drops. So as you get a higher amount of heat, the band gap gets smaller, you promote more carriers. This means that the open circuit current increases and the open circuit voltage decreases, and this decreases your efficiency of your solar cell. And also explains why the temperature affects the efficiency of your solar panels. So that's another effect on the efficiency. Unless it's absolute zero, you're not getting the maximum efficiency. Another area taken into account is spectrum losses. So let's assume we're getting our light from the sun, which most solar panels are. The light comes to us in a range of wavelengths. So you can think about these as the different colours, but it extends far more than the colours that we see, going from blue to red. We also go into the infrared, we get radio waves, and off the other side we get ultraviolet and eventually things like gamma rays. So when the light that can be used by a solar cell is dependent on the band gap, so the difference between that valence band and the conduction band. And light depending on its colour, has different energy. So blue light has more energy than red light. So if your band gap is too big and you try to excite an electron from the valence band to the conduction band with red light, it won't make it up to the conduction band, and therefore you won't be able to generate your electron hole pairs. So you need a smaller band gap to absorb more of the electromagnetic spectrum. So silicon it can absorb anything up to the infrared. However, if you have blue light exciting, that excess energy doesn't promote more electron hole pairs. What effectively it ends up doing is just being given out in terms of heat, or with more electron interactions in the conduction band. So there's some energy wastage there. So it's a trade-off between having a small band gap to take in the widest possible spectrum of light, and also having a band gap which is larger, so more of the light is actually used and you get less electron energy losses. So Shockley-Queisser actually calculate this to be 1.1 eV, which is actually what silicon is. However, due to silicon being an indirect band gap and also other problems with electron transport through the material, and when you take into account other effects, it's actually about 1.4 is the ideal band gap. So that's the main components of the Shockley-Queisser limit, and this places an upper limit on how effective our solar cells can be. So now let's have a look at what actually affects the solar panels on our roof. Why aren't they 100% efficient? So there's a number of reasons for this. First of all, that the solar panels on your roof are made up of individual solar cells. These have been getting bigger and been getting higher quality with the movement from amorphous silicon, which has lots of grains in it, through to single crystal, which means the electrons can travel through it easier, which means when you want to extract your current, it has less boundaries to transport across. So think about this as having a pipe with lots of little connectors in it. There's more chances of leaks. So if you have one big solid pipe, it's better. So that's one improvement, now hence one of the reasons why silicon solar panels have been improving in efficiency. We also have other design problems with our silicon solar panels. So if you look at your solar panels, you'll see those sort of silvery lines, so those are the top contacts. So that's how you get your electrons out of your solar panels and to your load or to your house. Those wires are conductors, but they are also acting as a shade to the silicon solar panel underneath. So not all the light that hits the whole unit is actually hitting the active part of the solar panel because of that shading. The problem is, the smaller you make those wires, the more resistive they are and the more energy you lose. So again, there's a trade-off there. So you can see how this becomes a complicated system. We also have the issue of reflection. So light hits the solar panels and reflects off. Most of it gets absorbed, but some is reflected. So there has been headway made in making solar panels more absorptive or less reflective. So you have anti-reflective coats on top, which can be a material, or it can actually be made by making the silicon rougher. So rougher surfaces reflect less than smooth surfaces. So there's been some movement, some progression there. We can also think about the light going through the solar panels. Not all the light is absorbed in that depletion region. Some of it will transfer to the p-type layer underneath if you're going from a p-type layer at the bottom. And that light then might be absorbed by the bottom contact. Again, you can make that bottom contact reflective to reflect the light back out and back towards the depletion region. So there's been work done on that, but again, all this affects the efficiency of your solar panels. And then we've just got the idea of semiconductor physics and crystallography. So no crystal is perfect. It's very difficult to make a perfect silicon crystal. So you have defects, and what these defects can do is cause recombination. So these can be things like Shockley-Hall recombinations, where your electron travelling towards your conductor to be transferred to your load can meet a defect and then recombine with a hole there. And again, that reduces your efficiency. These defects are particularly prevalent near the surface and under the contact, where you can get lattice strains. So again, more work has been done to improve this. So I'll make another video which really goes into these methods about how you can increase doping under contacts, how you can add a pacification layer to help reduce reflection and also reduce recombination at the crystal surface. Anyway, that is basically a video that explains why solar panels are silicon single junction solar panels are limited to about 33% efficiency, and why the current solar panels that are going on your roof are only about between 20 and 25% efficient, and that number is creeping up slowly as developments are made. Hey, thank you for watching. As I say, hit that subscribe button. I'll see you in another video very soon.